yours. Thank you very much.
Great. Thanks very much. David, can you hear me okay? It's okay?
Yes.
Perfect. Okay, so hello to everybody. It's my very great pleasure to present this joint work, which has been carried out in the framework of an ongoing European project with 5 other partners. There are a lot of words in the title. What I really want you to take away is the idea that we're trying to build hardware platforms for edge intelligence using all the opportunities that we think are afforded by 3 emerging technologies. So I'll be introducing junctionless vertical transistors, ambipolar transistors, and ferroelectrics. And the idea is that we want to put this all together into a very energy efficient 3D compute cube that gives us easy ways of assembling these structures to make a complete solution for machine learning and artificial intelligence. Now, before we get going, I'd like to motivate the talk, and I guess that some of you know these films, so Star Wars. One of the things that really hit me when I first saw this when I was a young boy is that this scene very early on in the very first film shows an alien, Greedo, talking to Han Solo in his own language, and they seem to converse very easily to understand what is going on. And so this really bugged me when I was a little boy. This is me when I was about 7 years old, well, probably a little bit less than that, but I had a lot of questions at the time, and I was trying to figure out, how did they learn all these really weird languages? And over time, I came to come up with a more plausible hypothesis that it's actually an in-ear translation device. So they don't actually know all the languages, but they have a device which enables them to understand the languages. Fast forward a few decades, and we now have an in-ear translation device which actually exists. So there are these earbuds that you can buy for about $200 on the market, which communicate with your mobile phone via Bluetooth, and then the mobile phone communicates to the data center where the actual translation work is being done. And it will use a machine translation model, which is probably going to be having at least 100 million parameters on 32 bits with the same number of max per inference, 95% accuracy rate. Then that feeds back the results to the earbuds. And there is also an offline version of this, which downloads some of the model onto your phone, but it still requires this interaction between the earbuds and the phone. Now, this is very good. This is an amazing advancement. But does this actually hit what is going on Tatooine? And the answer is probably not. What we see in the film is that this solution we have on the right needs the cloud. And so there are some very difficult things which have to be overcome, which probably would be deadly for Han Solo. So could latency nullify Han's lightning reflexes and mean that he would be in danger from Greedo? Maybe Jabba could hack the communication to find Han and then send some assassins to get him. And the final question is there even a signal on Tatooine? The 5G signal is probably wrong. So we think that there is probably something more behind this. So how could we do this without resorting to the cloud and using all the compute power that we could have accessible in a real in-ear translation device? Well, this is quite a general problem that we have today, and it's called edge intelligence. We've heard a lot about moving AI to the edge, and we know that it is not possible for the very large-scale, extreme-scale AI models that we have today. We saw yesterday in Valeria's keynote that one of the natural language processing and computer vision models is at least 10K larger than the 100 million parameters that we were talking about there. So WuDao 2.0 has over 1 million parameters, and this is obviously not something that we're going to be able to put into the edge. And in fact, when we look at the cloud, where classification and training is done in these massive high-performance computing data centers, we see that the carbon footprint is exploding, and a lot of this energy is actually coming from data transport, not just from the edge,
sag mal, das war ja wieder komisch, oder?
Inside the cloud itself.
Oh.
And the issue is that we have this alarming statistic that AI energy is actually doubling every 3 to 4 months. So the answer would appear to be clear. We have to move the intelligence to the edge to avoid all this data transport and avoid using these data centers in the cloud. But of course, there are constraints. Edge AI with fairly advanced technology nodes. The models that we can do are limited to a few tens of millions of parameters, let's say, due to storage and computing constraints, and also due to size, weight, and power constraints. And probably the power constraint, the energy constraint, is the most stringent, because the energy consumption has to be very low, and the power consumption also has to be very low, and particularly for the in-ear translation device to avoid burning the ear off when you try to do some intensive translation. So our answer to all this in terms of hardware is going to a mix of emerging technologies. And so there is this Horizon 2020 program, which is ongoing, where we're looking at mixing non-volatile aspects to build non-volatile logic with ferroelectric devices, vertical devices as well to get to some very compact and energy efficient logic cells, have some versatility using antipolar transistors, and then building up to this N2C2 concept so that we can get to a scalable and versatile 3D cube that can then be put together into a complete architectural accelerator system. There it has a physical regularity, functional versatility, and we can do some hardware software co-design and try to also apply some approximate computing techniques for machine learning. So I'll try to walk you through in the 20 or so minutes that are left. Why are we looking at vertical technologies? Why ferroelectric? Why antipolar? What is the motivation for putting these together? As it is an extremely vertically structured project, there is also an extreme interest in looking at design technology co-optimization from the application down to the real technologies. And then we'll get on to some more architectural aspects with the neural network compute cube, how we put it together into a systolic array kind of architecture, and show some preliminary results on the application of transformer-based models. So vertical, why vertical? Well, the vertical transistor technology is not a new idea. Here we see some lab demonstrations of this, which come from a few years ago. But the idea has been around for a while. The idea is that today, as we hurtle towards the end of Moore's law and lateral scaling, it would be maybe a good idea to try to switch things by 90 degrees. And then we can get to a device in which the minimal gate length is not actually limited by lithography resolution. It's limited by the material thickness, which you can control down to much smaller dimensions than lateral dimensions. And it also makes possible stacking of multiple devices in series. A very straightforward way is just by adding a gate onto the nanowire, the vertical nanowire. Do that in the vertical direction. And so the combination of these means that scaling can continue. We get to smaller devices, which can be put into more compact footprints. So gate capacitance and device-to-device wiring capacitance is reduced. And this is the key metric which enables energy efficiency to be improved. So increasing performance and reducing energy. So it's not a new idea, but interest has renewed recently. We've seen it in the IRDS for the past few years or so. The vertical nanowire FETs belong to the gate all-around FETs, either lateral, which we see here, or vertical. And very recently, at the beginning of the year, we actually saw some announcements from IBM and Samsung about their work on these vertical FETs. And they were looking to get to more smaller, more powerful, and more energy efficient devices. So this is the kind of thing that we're looking at. Well, we did some analyses on the energy delay product of basic logic cells. And what that actually shows, energy delay product is a key metric to understand energy efficiency in logic. And we were comparing this to the FinFET-based realizations. And so we tried to change some geometric parameters in terms of the device characteristics, such as the gate level compactness, the nanowire radius, the spacer length between the gate and the drain, and the gate thickness length as well. And what we see is that in comparison to FinFET-based structures, we can get to some extremely interesting gains, at least a factor of 10. 10x is relatively easy to get to, when you have a fairly low nanowire channel length. But for most of the physical parameters that we're changing, we were actually getting to fairly high numbers, like well above 10, up to 20, even to 40. And the conclusion is that this actually gets better as we scale down. So this enhances the view that scaling can be improved by this vertical aspect. So the smaller and fewer nanowires per vertical nanowire FET, we get improved performance comparisons. Let's move to another flavor of the emerging technology, the ferroelectric. Well, ferroelectric, as many of you already know, is a non-volatile memory technology. It actually, in comparison to other non-volatile memories, gives a best-in-class energy efficiency. We can see this here, where you have two categories, basically, of ferroelectric memories, either back end of line for the FERAM or front end of line actually integrated into the gate stack in transistors as a FEFET. And you get orders of magnitude improvement. 10 femtojoule per bit is way less than the other picojoule bits that we get in other kinds of memory. It's also hafnium oxide based. This was actually a game-changing observation about 10 or so years ago, that hafnium oxide could be either doped or strained to give ferroelectric hysteresis characteristic. So it means that it's intrinsically CMOS compatible, because hafnium oxide is already in the production line for CMOS. And it's also VNW FET compatible, as was actually demonstrated a month or so ago by our colleagues in China in this publication. So this shows us that we can move to memory cells, of course, but also, and more interestingly, in my point of view for AI and machine learning, get to some non-volatile logic cells and therefore address in-memory computing. So we looked at some back of the envelope graphs about how in-memory computing, near-memory computing and GPUs compared to a baseline CPU, implementation of matrix multiplication. This is the key operation that we want to do in machine learning. So for this kind of complexity of operation, we're transferring the matrix coefficients, which could be stored in a non-volatile part, to various degrees of proximity to the CPU. Made some assumptions in terms of communication and computation costs, as well as the programming costs that we saw in the previous slide. And what we see is that we're going in the right direction. As you move the coefficients closer to where you're actually doing the computing, things improve. So we're getting to some extremely high, interesting results in terms of energy reduction with respect to the baseline CPU, even when you're in near memory computing. And in-memory computing goes even further. And in terms of latency, then this also improves. Of course, the numbers are very dependent on the actual hypotheses that we use, but the tendency is obviously clear and extremely interesting as we increase the matrix dimension, which is what happens in complex and high-level AI models. So, for example, a non-volatile logic cell can be built fairly easily, actually, with these non-volatile FEFETs. And this particular function is an XOR. XOR function is a key operation when you want to do addition. Obviously, it's the sum characteristic, it's the sum output. So adders are also used in multipliers, and both are used in Mac units. So an XOR operation is really key. And the idea is to be able to program one side of the coefficient. So for example, A would be stored in the non-volatile part, and this changes the characteristic of the device. And then you can then process B, the other data which is coming in at speed. And so this has absolutely no impact on the actual calculation. So you're doing things a lot faster and in a more energy efficient way. So this was published a few years ago by our friends in NAMLab. This is an NMOS logic gate using a junctionless ferroelectric single gate stack. Static CMOS logic style is here, where you have N-type and P-type FEFETs. And then you can also extend this to stacking two gates on top of each other, two ferroelectric gates on top of each other. And this gives you also a very compact structure, because instead of having, for a 3-input XOR, 20 individual devices, you only actually have 8. So the compactness of the solution is clear. Yeah, the third technology is ambipolar. Again, some of you already know this. Ambipolar enables reconfigurable transistors. Now, by reconfigurable, we mean switching between N-type and P-type via electrostatic doping rather than chemical doping. An additional gate is necessary for this. So for GX, which would be G1 or G2 in this cell, you program the type of the transistor either to N-type or to P-type. And this work, which is illustrated here, was published about 10 years ago at DAC by our friends at EPFL. And they basically put 2 transistor pairs together and enabled a set of logic functions through the connection of each dumbbell contact to various points, either ground, outputs, VDD, or the inputs. And the idea behind this is you can tune the hardware really to your application needs. So the vertical version of this that we're doing inside the Full Monty project uses the ambipolar 2 stack gates implementation of the transistor. We could also add into that the ferroelectric to store in a non-volatile way the state of the polarity gate. This is also an additional possibility. And this gives us these kind of tiles, which are also much more compact than the lateral version. And if we compare the size of these tiles to the explicit XOR2 implementation, also in vertical, using a single gate stack or double gate stack, then we also get a very strong footprint reduction for the XOR2 configuration of these gates. So that's the 3 technological variants that we're trying to mix together. So this requires an extreme contact and communication between the technology guys, the compact modeling, the TCAD guys, the circuit people, and the architectural exploration. So what has been done in the project is going at least at the middle from a scripted 3D cell generation. So it enables us to explore very quickly a number of possibilities at the physical design level of the various cells. It can then export GDS2 that can then be imported into one of our partners' tool sets who work both on TCAD and on parasitic extraction. And then the TCAD enables development of a compact model. The parasitic extraction enables the compact model to be enhanced with more realistic structural data. And then we can use this input to do some library generation for logic cells using a designer experiments to basically characterize the library. And then we use these characteristics in logic synthesis to go to benchmarking and do this quantification of energy and delay metrics. So it's complex, but it's feasible, and it's now in place to do this. And it's also enabled us to look at some physical design space exploration. In particular, in terms of the physical design, one of the things that we identified is that yes, Manhattan routing between cells is interesting and it's conventional, but the way in which things have been built means that it may also be good to call that into question and allow octilinear routing styles. So this is an example of the exploration that we've undergone, and looking at various cells with varying number of transistors. And we can show that Manhattan routing is not particularly efficient, and it can actually be vastly improved if we use this kind of octilinear approach, either with single gate or double gate stacking. Okay, let's move on to the N2C2, the compute cube itself, where we're looking to build this very flexible computing hardware block for neural networks, and more particularly for transformer-based neural networks. So the idea was to be able to configure lots of things. Configure the function. We know that we need to do this kind of multiply, accumulate, and activation function, but we also wanted to be able to switch things in and out. So do the map or the multiplication or the addition, and be able to switch in or out the activation. And we also wanted to be able to enable exploration of approximate computing techniques. So we wanted to also configure the data width. So we have a mechanism which enables us to either do computing on a 32-bit integer or to scale down to do 2 16-bit operations or 4 8-bit operations, etc., and also to scale up to connect the N2C2s together to scale up to 64, 128, 256 bits. And so this is the structure and the basically the mode of operation of the N2C2. And then putting it together means that we're basically trying to compute matrices of n by m dimension, but in the actual computation, the matrix size can be different, and it involves this k part in which we also have to affect some resources, so N2C2 resources, to resolve the elements of the n by m matrix in a certain number of cycles. So functional simulation was proved. We've connected 4 N2C2 blocks together to compute one matrix element. So you can see here the data and the weights. We then have the partial outputs and then the complete output. And the various N2C2s can be configured to different functions. So one would just do a multiplication, and then the rest would do the multiplication and accumulation. And so this does do the computation in a single cycle. And this is the result that we get from a 32-bit integer computation. This particular example is fairly easy because it doesn't involve any overflow. But of course, if we're doing the integer computation, then at some point we will need the overflow. This is the characteristic with respect to floating point. So we have also implemented an overflow management policy for this based on saturation. Now, the idea, actually, if we go to how this fits together into a complete accelerator architecture, is that it actually is an implementation of a systolic array. A systolic array is a homogeneous network of very tightly coupled hardwired data processing units. And the data processing unit, the DPU, is actually these N2C2s. So it's very well adapted to dense linear algebra computation, as we're doing in machine learning. And the idea is basically that each individual cube in its own world will receive partial results from data upstream. It will generate the result, save it, store it within itself, and then also pass the result downstream. And so this means that, for example, if we have weights as B and A as data, that B will be shared across the rows and A would be shared across columns. And these could then be put into a non-volatile weight. So the systolic matrix multiplication that we're doing has the advantage, because we have this very well connected and densely dense computation accelerator. It means that we improve the time that we need to run the operations. In the experiments that we ran up till now, we've considered that the implementation is weight stationary, so the weights can be non-volatile, and the input stream comes in horizontally and the outputs come vertically. Now, in transformer-based networks, in general, we have very large sizes of matrices, and this is a common problem. We expect that matrices will not fit directly into the hardware resources, that it will not be possible to do this static mapping of the complete data. So we had to explore also how we map the matrices onto the hardware resources. So we use a reasonably sized accelerator, and so 8 by 8 or 16 by 16 N2C2s. And then we're basically dividing the computation into time. So the matrices get split up into tiles. We process one tile at a time, store the partial results, and then aggregate them along the computation. For this work, this is done actually at EPFL. They were using their Gem5X system simulator, where we modeled the accelerator as a custom functional unit and extended an instruction set architecture coming from ARM to some custom extensions to handle accelerator implementation. Now, the main kernel is matrix-matrix multiplication. This is used in some of the input stages, most of the input stages. Some of the nonlinear stages of the output are less workload intensive. And so we focused on this particular part here, and we compared the inference time and the number of memory access based on the type of accelerator architecture that we're using. So baseline is a conventional non-accelerated ARM single core, and we then used kernels of varying sizes, 4x4, 8x8, or 16x16. And you can see that that we get some fairly good results where we have a 10x speed up in the inference time of a transformer block when we use a 16x16 kernel, and the number of memory accesses is also significantly reduced. So to wrap up, and I hope I've held the time. So three technologies that we've been looking at: the vertical transistors, which show a 10x EDP reduction, 10x for 40 nanometer vertical nanowire FET gate length. Also ferroelectric in memory computing, which showed both 10x energy and 10x latency reductions with respect to a CPU-based approach. And then the ambipolar, which hasn't been quantified in terms of the energy and latency reduction, but it gives access to very compact, flexible, and disruptive logic cells. And finally, the architecture, the accelerator, the N2C2 approach gives a 10x inference time reduction. So looping back to the Star Wars theme at the beginning, this may be a new hope for hardware accelerators for machine learning. If we put everything together, the 10x's that we get everywhere, then we could hope maybe that we can get to improving energy efficiency by 4 orders of magnitude up to 10K. Thanks very much for giving me the opportunity to speak. And also thank you to the people who've worked on this. Thank you to the team, in particular, Alberto and Bastien Central, Giovanni and Alireza, EPFL, who did a lot of the work on the N2C2s and the accelerator exploration. And a quick plug, we're also hiring. So if you're interested by the adventure, if you'd like to do a postdoc on this project, then please get in touch and let's talk. Thanks very much.
Thank you very much, Ian. Thank you for the great talk. Questions from the audience? We have still time. A couple of minutes, I would argue, because we are started a bit late. Don't see if anybody wants to talk, we can actually unmute. So I have actually had to mute all of you because I saw there was some noise in the background. So I decided to mute you all to avoid any troubles. But if you want to ask a question, you can unmute, or otherwise you can ask on the chat.
I can't believe it was so clear.
No, I have a question even for myself, so I can actually ask you a question, if you don't mind, Ian. One of the sure. Points was when we talk about the integration of this technology with respect to traditional, let's say you take a normal FinFET and 7 nanometers and so on. Okay, well, there's a lot of effort on integrating these new designs and so on. So is it something that you think is reasonable, that companies will actually in the end agree to actually move in this direction? We need to get a lot of benefits to be able to increase or justify this change, right?
Yeah, I agree. And at the beginning of the project, we actually discussed how to position the technology. And I know that a lot of people, if we go back to, for example, the initial IRDS, this vertical technology is perceived mainly as being complementary to lateral gate all around, and in particular useful for doing access to memory. So it could be used as a back-end of a selector device for back-end of line memory. And I think this is what IRDS is seeing the use of vertical technologies as being for. I believe that this proves that the co-integration of vertical with lateral devices is possible, that it's definitely something which is feasible. Now, the optimization of the device will be different if we're using it as a selector device rather than a logic device. I think that the integration possibility is definitely there, that there is possibility also that we could do a logic device as well. But I think that, yes, the co-integration part is key, for sure.
Okay. Thank you very much, Ian. So if there are no more questions,